Chapter 9 Exercise Set, Problem 3. The following observations are made on fracture toughness of base plate of 18% nickel maraging steel in C square root of inches. By the way, this data set came from Fracture Testing Weldment ASTM Special Publication number 381, 1965, which means these numbers are not made-up numbers for classroom use. Rather, they are part of a real-world, real-life application problem. In this case, it is for the material science or metallurgy. In any case, here is the summary of the sample statistics. There were 22 observations, right here, and you can find out the sample mean and sample standard deviation with these 22 numbers. If you do, you're going to get these numbers, 77.33 and 5.037 approximately. Okay, let's begin the problem. Explain why the t-curve is more appropriate than the z-curve in this case. By the way, this is the hardest problem. Number 1 is the hardest. And this problem came before the others not because it's easier, but because this is a necessary step. Now, how do you tell this is a t-curve problem? One number stands out, n equals to 22. Oh, small sample size. Less than the threshold of 100. Okay, that's a good reason. But that's only one of 3 criteria that you have to check. How about the other 2? Well, here we go. Criterion number 1. The original distribution is believed to be normal. Yes, in this case, because this is an observation. There's some observation error, either in plus direction or minus direction, but a bulk of them around 0. So the original distribution is more or less normal. It checks out. The second criterion, the original standard deviation is unknown. In this case, closer to unknowable as a matter of fact. If you have really large population size, then original standard deviation or population standard deviation is difficult to find. In this case, the sample size is infinity because this is out of observations, so you can do as many observations as possible. So sigma value is impossible to get. We have to use sample standard deviation. How about criterion number 3? This one everybody remembers. The sample size is small. 22 is way less than our threshold of 100. Even if you use kind of cheating and use threshold of 30, it still works out. But I don't like using 30. 100 is usually the best. Okay, in any case, we can check out all these 3 criteria. By the way, a little of digression. Why is this important? Original distribution has to be more or less normal. For example, if you roll a die 5 times and then try to analyze it with t-curve, that's not going to work because the original distribution is no way close to normal. How about this aspect here? The original standard deviation is unknown versus it is known. That's something we are going to discuss in problem 4, an optional problem. For most of the students, you don't have to worry too much about that problem number 4. Anyway, the first problem is done, and that was the hardest problem. The other 2 are going to be better because they are more or less algorithmic. Let's go. Based upon the study, find a 99% lower confidence bound. Okay, what do you mean by this? You're looking at this kind of picture, lower confidence bound. So we have this outline, and the center is, of course, the expected value, observed mean of 77.38. Now, 99% lower confidence bounds, lower, so you have to go to the left, go lower, go down. And 99% should be in the middle, and then the other side, and 1% over here in blue part. So that's the picture, and this is the value you're looking for, the end value. How do you find it? We use the formula number 1, end minus center over SE. Here we go, end minus center over SE. So x minus center of 77.33 over standard error of ST over square root of n is equal to appropriate t value, and you have an equation. Now, what is that t value? How do you get t equals to negative 2.518? Let's find out. Here's a t-table, and let's go to the degree of freedom of 21. Okay, we have it here, and then we have to go to 1%, the tail part, and here we go, 2.518. So that's your t-score. But there's a bit of a wrinkle here. In this t-table, shading is to the right. And from our problem, shading is to our left. Consequently, we need a sign change. That's why we have negative of 2.518. I emphasize it in different color here. Okay, we are all set. N minus center over SE is equal to t-score. So let's solve this equation. First, flip the denominator to the other side. So t-score times SE. And then flip this center value to the other side, and we have this computation. Center value 77.33 minus t-score of 2.518 times SE. If you calculate it, you're going to get this value, 74.65 something. By the way, what if you don't see this negative sign? Suppose that you just made a sign mistake. That is, from the t-table of degree of freedom 21 and 0.01, okay, 2.518, and let us suppose you just blindly used it. In this case, you're not going to get this negative sign, so you're not going to get this negative sign, and this will be plus consequently, and you end up making this kind of mistake. So this is plus, and then run it, and you're going to get 80 point something. Now, if you don't have your picture and then write down this value and then move on, you're going to lose a lot of credit. However, I really emphasize the picture. So if you come back to the picture, you can easily see your mistake. Center value is 77.33. You have 80 something here to your left. At this moment, you should be able to see that you just made a sign mistake. No sweat, let's go back to that sign and put this extra negative here, which I highlight in this red color, and we get this negative and this negative, and in this computation, change this to negative and run it again. There you go, you have your answer. Finally, here's the conclusion. Lower confidence bound and all the answers as well. Okay, so much for confidence bound. Now let's do confidence interval. We have to find two endpoints this time. Estimate the 95% confidence interval. Okay, let's do that. And the correct picture looks like this. Interval begins from here, x1, and ends at here, x2, and 95%, so here's a bulk in the middle, 95%. The rest of this is 5%, and it has to be shared by the left-hand side wing, 2.5% here, and right-hand side wing, 2.5% there. Which one do we find? For z-curve, I usually went for this blue, but for t-curve, I'd like to find this red one as well. I'd like to find this red one first, and then find out the blue one later using the symmetry. So let's go with this one first. How do we do that? The same idea, end minus center over SC equals to the t-score. Here we go. End minus center over SC, which means x minus the center of 77.33 over standard error, s over square root of n is equal to appropriate t-score. How do you get this 2.080? Let's find out. Let's go to the t-table. Okay, here's the t-table, and we need shading here, 2.5% to our right. And that means we have to follow this column here, 2.5%. And let's go down to the degree of freedom of 21, coming right here, and that is 2.080. That's your t-score, 2.080. That's what you put over here, n minus center over SE is your t-score. And let's solve this equation. First, flip over the denominator by multiplying it, and then flip over the center by adding it up, and this is what I get, 77.33 plus the t-score of 2.080 times the standard error of 5.07 over square root of n. Calculate it out, you're going to get this number, 79.56 something. That's this x2 value. How do you find out this x1 value to the other side? Well, just use a symmetry. Change this plus to minus, and then run your calculator, and you're going to get the answer, 75.0963 approximately speaking. And here is the conclusion. The 95 confidence interval is from 75.1 to 79.6, and here's a full picture, 95% here, 2.5% here, 2.5% there. Want to see the computation again? Here we go. N minus center over SC is t-score, and then just use the algebra, and then we have x value, and then change the sign using the symmetry, the other x value.